Welcome back to the episode 5.16 of our video course Parallel Programming and Optimization with Intel Xeon Phi coprocessors. We discussed single-node tuning in the earlier episodes in this chapter. The discussion in the last 3 episodes will be about optimization topics for applications in distributed memory systems such as clusters and heterogeneous systems with coprocessors. When your application has to scale across multiple processors and coprocessors, the obvious point of interest is the efficiency of communication. Let's talk about using coprocessors first. The first consideration with coprocessors is whether you should use offload or native programming. When you're using Intel Xeon Phi coprocessor of the first generation in the offload mode, you can expect to transfer data to and from the host at around 7 GB per second. If your application is compute-bound, then the ballpark estimate of your performance is 1 teraflop per second. In double precision, this translates into 8 terabytes of data per second delivered to the cores. So there is a factor of 1000 gap between how fast you can send data into the coprocessor and how fast your vector units can process it. As a consequence, you can predict how significant the communication overhead is going to be for any specific algorithm. Suppose your data size is n, and your algorithm has a complexity of n squared. This means that for every number that you offload to the coprocessor, you will perform n squared divided by n, which is n, operations. Clearly, the larger the problem, the more operations you perform for every data element that you transfer, and for n around few thousand, communication should be insignificant. For instance, if you do matrix vector multiplication where matrix size is n by n, but you retain the matrix on Xeon Phi and only transfer different vectors, you can expect that offload will pay off when n is of the order of a few thousand. However, for small values of n, offload will be too expensive, and it is better to do the operation on the host. Now consider another example. Your data size is n, and your algorithm has a complexity of n log n. This means that for every number that you offload, you will perform n log n divided by n, which is log n, operations. Even if n is in the thousands, you perform only tens of operations on each number that you send, so the overhead of offload will be significant. For example, if you want to use offload to compute fast Fourier transforms that have the complexity of n log n, you should expect that data movement will take a significant amount of time. In this case, one of the optimization strategies may be to modify your code so that you generate data on Xeon Phi instead of offloading it. Another consideration for offload is that when you move data, you have to move it efficiently. We discussed in the episode about the explicit offload model that by default the runtime offload library will allocate a memory buffer on Xeon Phi for your data and deallocate it at the end of offload to clean up. This is inefficient because memory allocation is a slow serial operation. If your application performs many offloads, you need to make them more efficient by using clauses alloc if and free if to retain the memory buffer on Xeon Phi between offloads. This plot shows the effect that those clauses have on performance. The red line shows the data movement time for the default case when the library performs memory allocation and deallocation in every offload. In this test, we do not do any computations, only offload data. For even the smallest offload data sizes, you have to spend up to 1 millisecond on offload overhead, and for large data sizes, you achieve a bandwidth of order half of gigabyte per second. The blue line shows the offload time for the case where we used alloc if and free if to retain the data on the coprocessor. In this case, the overhead of offload for the smallest data size is of order of 10 microseconds, 2 orders of magnitude better than in the default case. The bandwidth for large offloads is of order 6 to 7 gigabytes per second, which is an order of magnitude better than in the default case. Finally, the third consideration for offload efficiency is masking communication latency behind computations. When your application is organized in such a way that you perform many consecutive offloads, you can stage data movement and computation so that they overlap in time. If you use the explicit offload model, you can do it using asynchronous offload as we discussed in episode 3.7. This image shows 2 timelines to illustrate an approach called double buffering. Suppose that we have a batch of tasks and we perform offload to a Xeon Phi coprocessor for each task. With default blocking offloads, we will offload the first dataset and perform computation on it, then offload the next dataset and compute, and so on. If the data movement time is comparable to computation time, we may end up paying too much for offload in terms of performance. The second timeline shows the double buffering approach. In this approach, we will allocate two buffers on Xeon Phi that feed two datasets. First, we will offload the first dataset into the first buffer, then we will start computation on this dataset on Xeon Phi, but we will do it asynchronously. This will allow us to simultaneously start data movement to offload the next dataset. When computation completes, we will start computation on the next dataset asynchronously. And at the same time, we will start retrieving the results of the previous computation and offloading the next dataset. We will have to switch between two buffers as we do this. This is why this method is called double buffering. This procedure can be implemented using the clause signal in Pragma offload and using the specifier into. You can see an example code that performs double buffering among the labs of our book. This code performs matrix-matrix multiplication on a set of not very large matrices, but the procedure can be generalized for any workload, not just matrix-matrix multiplication. Performance results show how first implementing memory buffer retention and then implementing double buffering helps us to increase the performance of the application. For details, you can refer to the section 4.10 in our book. In the next episode, we will talk about optimizing communication once again, this time discussing communication in MPI. If you have any questions, leave them in the comment section below the video. Thank you for tuning in, and I hope to see you in the next episode.